Namaste. Hope you're doing well. Today we will solve the second question of ISI MSTAT 2022 PSB. And on face value, it is a linear algebra problem involving eigenvalues. So you are given a matrix and you have been given some conditions about it. Positive trace. Trace is the sum of the diagonal elements of the square matrix, and determinant is negative. So first, we have to show that the matrix must have at least two real eigenvalues. Now, okay, before we begin, we have to get a relationship between the 4 cross 4 matrix and its eigenvalues in a way that does not require us to deal completely with the form of the 4 cross 4 matrix. We don't want to go in this direction. It's going to be lengthy. So is there a way to connect eigenvalues and the trace and determinant? Thankfully, there is. Smart people before us have established these two relationships, wherein the trace of a square matrix is the sum of its eigenvalues. In this case, 4 eigenvalues because it's 4 cross. And the determinant is the product of the eigenvalues. Perhaps these two are the most beautiful results in linear algebra when we're dealing with eigenvalues. And we'll soon see why they are going to help us. Now we have this relationship with eigenvalues and the matrix. Now we have to show something, prove something to be true. Because the question is asking us to prove it to be true, it means it has to be true. And this is why one of my favorite ways to go about it is proof by contradiction. Because you start by assuming the opposite of the condition that's given, and because the original condition has to be true, when you assume the opposite and play around, you are bound to find something that will contradict the initial conditions given to you in the question. That's the subtle motivation about proof by contradiction. Now, the statement is A must have at least two real eigenvalues. The opposite of that is A need not have at least two real, or rather A does not have at least two real eigenvalues. It means A has zero real eigenvalues. It means all the eigenvalues are complex. So this is the starting assumption that we take. And then we give a structure to the 4 eigenvalues. Pretty standard structure in complex numbers. A plus IB, A minus IB, C plus ID, C minus ID, A, B, C, D are all reals. And I is the iota square root of -1. Now that we have it, let's look at the form which is taken by the trace and the determinant. The trace is the sum of the eigenvalues. And because the eigenvalues, when they are associated with the real matrix, come in conjugate pairs, which means a structure where when you add the two conjugate pairs, the imaginary parts get cancelled. So that's why when you take the sum of this, only the real parts remain, twice of the real parts remain. So this doesn't seem to give any sort of contradiction. But when you look at the determinant, which is the product of the eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4. Yeah, by the way, lambda 1 and lambda 2 are giving this, and lambda 3 and lambda 4 when multiplied are giving this. And this is because of the way iota, this I works. Let me just give you a quick illustration. This is this, right? Which is this. Now I square is the square of this. So it becomes -1, which ultimately becomes A square plus B square. And similarly C square plus D square. Now, this is non-negative. This is also non-negative. Product of two non-negatives is non-negative. So if we assume every eigenvalue to be complex, it means that the determinant is non-negative. But The question says that the determinant has to be negative. I don't, when you play around, something will come up that will give you a contradiction. And in this case, this is the contradiction. And a more detailed English version of what I just said is over here. And with this contradiction, we have that A cannot have all eigenvalues as complex. And hence, the opposite of this is true, which means A must have some real eigenvalues, and the minimum possible real eigenvalues that A can have is 2, because complex eigenvalues occur in pairs, so they can be having an even number in terms of their presence only. So they can be either 0, 2 or 4. So we have it. The second part is show that A can have non-real eigenvalues. Now, I don't know whether to you it is vague or not, but to me it's vague. And clubbing it with the information from the first part of the question may help us, because honestly, that's how the question makers structure the questions. So you have this proven from the first question. And when you combine this information in the second question, what you get is A must have at least 2 real eigenvalues. And you have to show that A can have non-real eigenvalues. So you have at least 2 real eigenvalues. And to show that you have non-real as well, you must have the minimum being complex. So 2 real and 2 complex. So the question boils down to, the second question boils down to show that A can have 2 real and 2 complex eigenvalues. So now it becomes more specific in terms of what it is asking. Now, in this case, we have to find a matrix or 4x4 matrix satisfying these conditions that has 2 real eigenvalues, 2 non-real or complex eigenvalues. And the way we can go about it is we can start building what we are asked. That is, suppose that A has indeed 2 real and 2 non-real eigenvalues. And then when we put more math into it, the motivation is to ultimately get some conditions that can link this structure back to the original conditions. And from there, we can sort of reverse the direction and then get back a matrix that has these conditions satisfied. In a way, it's similar to what we did in proof by contradiction, but there the motivation was to play around and get something that messes up the structure. And here the motivation is to clear out and get something that can link the structure and the condition. Okay, so you have 2 complex eigenvalues, 2 real eigenvalues without loss of generality. You can have this structure for your complex eigenvalues, and real eigenvalues are similar. Now, with this structure, this is going to be your trace and this is going to be your determinant. That is very easy. That's just addition and multiplication. Now link back to what's given in the original question. You need to have positive trace and negative determinant, which means this expression has to be positive, this has to be negative. And an interesting thing to get an answer to this or to solve this, you don't need to give a general proof that sort of shows that A can have 2 real eigenvalues and 2 non-real eigenvalues. You can get very specific as well, as in if you can show just one such matrix that can give you 2 real eigenvalues and 2 non-real eigenvalues and satisfy these conditions, then that matrix is in the class of matrix that is represented by A. And even one such matrix is proof that A can have non-real eigenvalues. And that is the motivation to not go beyond this general structure, but to sort of put values in it and simplify it. And now, if you notice, by getting rid of this A term, this would just boil down to this. And the simplest to go from this would be to take B as 1, which means your eigenvalues are completely imaginary and very nice imaginary eigenvalues, I and minus I. And the other two real eigenvalues, you can play around and get simple values. I have chosen 2 and minus 1 because 2 plus minus 1 is 1, which is greater than 0. And 2 into minus 1 is minus 2, which is less than 0. So that's it. If you can design a matrix which has these eigenvalues, then that matrix is a kind of matrix that A can be, and the existence of that matrix is proof enough that shows that A can have non-real eigenvalues. And the part now is to construct a matrix with these eigenvalues, and this is where we would use a block matrix kind of thing, and that's why matrix construction was a part of the prerequisite. Now notice that this is a block in the matrix, this is a block in the matrix. My motivation is to get a matrix A that has 2, minus 1 and imaginary I and minus imaginary I as the eigenvalues. We know that if we have a matrix A, then this determinant where equated to 0 gives all the eigenvalues of A. But when we have a block-like structure, this is A, and when we do this A minus lambda I kind of thing with it, we would end up getting A minus lambda I as 2 minus lambda, this lambda, this minus lambda, this minus lambda. And then we have to take the determinant of this. Now notice, if you start computing the determinant from here, you get 2 minus lambda times the remaining structure. In this matrix, it's just minus 1 minus lambda. So then you get you have to compute the remaining structures determinant 2 plus 2 over here. And that's product of this and this minus product of this and this, which is lambda square plus what? And when you equate it to 0, you get all the eigenvalues. So this structure, this kind of block-like structure where you have these nulls over here, this enables you to quickly have the matrix in such a way that getting the real eigenvalues is very quick, and you sort of have it in your mind that this thing, when you transfer it into an equation, the equation should give you the eigenvalue, complex eigenvalue that you want. Now, real part is sorted. Real part is sorted over here. So, in the remaining block structure, you can sort of look a little into the future and visualize that when you have this minus lambda over here, the only way that you would get minus I and plus I as the eigenvalues is when these two elements give you a product that is minus 1. So that when it is subtracted from lambda square coming from here, it becomes 1. So this sort of thing can help you construct a matrix which gives you the desired eigenvalues. So that's it. And some ways to build your base is to note that how conjugate pairs of complex numbers played a crucial role in this question, because without the information that complex eigenvalues come in conjugate pairs, you would have perhaps been stuck with the possibility of 1 real, 3 complex, something like that, and maybe you would have had to evaluate the entire 4 cross 4 matrix structure. And that's why conjugate pairs, when exist, they quite beautifully take care of each other complexity and make things really simple to deal with. And if you like this, if it was helpful, then the request is to remove unnecessary complexity in your life. Be more realistic. Okay. Take care. Hare Krishna.